Hey there, geometry students. Welcome to the lesson for 6.2. Today we are talking about properties of a special type of quadrilateral that's called a parallelogram. So properties of parallelograms. First we'll have to decide what a parallelogram is, or determine what that is, and then we can talk about some different properties from there. Alright, so make sure you're using those extra examples in your book. There's a few to go along with this one. We're going to do 3 examples together here, and it looks like, looking in the book here a second, it looks like they have 1, 2, 3, 4, 5, 6 other examples that you could look at in the book to help you out as you go along. So let's check this out. 6.2. First of all, let's decide, or determine, define. Can I come up with another D word for that? Decide, determine, define. I'm all out of D words. What is a parallelogram? So a parallelogram is just this. If you see that word parallel within the context, within the word itself, that's a good thing, because that's what it basically is referring to. It's a quadrilateral with both pairs of opposite sides being parallel. So it's a quadrilateral. Let's write that down, a quadrilateral with both pairs of opposite sides parallel. So let's draw a quick picture to go along with that. What's a parallelogram look like? You've probably drawn one before. I don't want to use red though yet. Let's see. There we go. So it looks something like this. It doesn't always have to be slanted to the right like this one is, but that's one way you can draw it. And then you're going to have, just to represent that it is actually parallel, I could have one arrow here with one arrow here, 2 arrows here with 2 arrows here. That's meaning those opposite sides are parallel to each other. So we've seen this before, that this represents, or it denotes that things are parallel to each other, sides are parallel. Quadrilateral with 2 pairs of opposite sides parallel is a parallelogram. Alright, so from here, I think, yep, I'm going right to here with that. So some theorems about parallelograms. There's 4 different ones that we learn in this lesson. So let's get those down here a second. Theorem 6.2, these really don't have special names, but they're pretty easy to write out what the theorem is. So theorem 6.2, 6.3, and we'll do 6.4 and 6.5 down here. And let's see what we got. So before we draw anything or write anything in, off to the right in each one of these boxes, let's draw some parallelogram looking shapes. We can't say that they are actually parallelograms unless we're told that they are, or that we have parallel sides, both pairs of parallel sides, but let's draw them all to look the same. So I have the I guess you could say a way to cheat and just move these things and copy and paste them. But you just draw on your own things like that, and oops, don't want that. But make them all look pretty much the same. Do all parallelograms have to look the same? They all have to look like this? No, you just have to have 2 sides, pairs of opposite sides being parallel. Alright, so what makes this, or what's something special about a parallelogram? We're assuming that these are all parallelograms right now. I'm telling you that that is the case. But what is something else you can say about opposite sides, first of all, here? So if you have a parallelogram, assume all these are parallelograms to start. So let's write that off to the side here too. For all these, we're going to assume these are all parallelograms. I forgot to add something in here a second, so let's do that here. The symbol. Instead of writing out the word parallelogram all the time, that gets kind of tedious. We have a symbol. It looks like a miniature version of this. The symbol always slants to the right, even though not all parallelograms will always slant to the right. But the symbol is that for parallelograms. And so So assume these are all parallelograms. If you want to make it plural, you can just write the little symbol with an S at the end. So we're going to assume that these are all parallelograms. Alright, so what do we have here? Theorem 6.2, we're assuming that these opposite sides are parallel. You can also say, if that's true, that opposite sides are going to be congruent as well. So this is a property about parallelograms that always holds true. We're not going to prove it, but it can be proven to be true. So opposite sides are congruent in a parallelogram. That's one property that always holds. What's another property that always holds? This is also going to be true. Pretty convenient. Nice that that works out all the time. So if you have a parallelogram, opposite angles are also always congruent. So opposite angles are congruent in a parallelogram. If you had this one and this one, these are not necessarily going to be congruent to each other, but I'm going to call this P. We'll go with key P, Q, R, and S. If you have a parallelogram, P and S, the two consecutive angles, any two consecutive angles you pick, they're always going to add up to 180. Alright, so this is kind of an example of this, that the measure of angle P plus the measure of angle S equals 180 degrees. So the big thing though to remember here is consecutive angles, they're supplementary. They're always adding up to 180. So consecutive angles are supplementary in any parallelogram. So in a parallelogram, that's always going to work. Another option you would have here, P plus Q, those two angles would be supplementary because they're consecutive angles, and they're consecutive angles in a parallelogram. Q plus R would also have to be 180, so would R plus S. And then theorem 6.5, it says this, I'm going to, yeah, I'll just freehand this, so, not my best work. I'm going to get out my drawing tool. No, not my best work either there. There we go. So I'm going to draw in the diagonals for this parallelogram. That looks better. And the diagonals in a parallelogram, they actually bisect each other. So this segment right here is congruent to this segment right here, and this one right here is congruent to this one right here. They are bisecting each other. Make that look a little bit nicer there. There we go. And so if we were to give these different vertices names, let's go with that in each one here. These weren't really necessary to talk about the letters of vertices specifically in these two, but it's a lot more helpful for sure in these two. So let's just write all those in. Down here we can say that QM is congruent to SM, and we can also say that PM is congruent to RM. And so what is this saying in words? It's saying that the diagonals bisect each other. In a parallelogram. So these are our four major theorems for this lesson. These are some properties that we can assume always hold true if you are told, or if you can assume, that the shape itself, the quadrilateral itself, is a parallelogram. So let's check out some examples to see what we have there. So I want you to draw a parallelogram in, and I'll make that a little thicker there. This one's still going to slant to the right. Remember, they don't always have to slant to the right, but you should be drawing them so that the opposite sides do actually look parallel as best you can. Alright, so we're going to assume that that is true. Let's actually draw that in here. We're making this assumption to start. And then I want you to draw in the diagonals as well. And let's give these points some names. Let's call this W, E, S, and T. That might make sense now. This is Jerry West. He's the guy on the NBA logo, actually. That's his silhouette on there. Very famous basketball player, played for the Lakers, and wore some very short shorts as well. So let's see, we got West, and then this M is going to stand for, you may have guessed it, the midpoint, because we just learned that diagonals bisect each other in a parallelogram. So we're going to assume that that holds true here because this is actually a parallelogram. And so if I told you that this was 4 and this was 6, you should be able to tell me what WT equals and what WM equals. So let's see. Can you do that? Can you look at that? What's WT going to be? We know that not only that the diagonals bisect each other, but that opposite sides are congruent in a parallelogram. So we can say this one is congruent to this one and this one to this one. So here we have ES is going to be congruent to WT. This is going to equal 6 then. This is by theorem 6.2. And so that's one answer. And then if I asked you for WM, we know that this and this are the same. And so we could say, let's actually draw that in, get out a different color if you haven't done that yet. And so let's put this in a different color. This one and this one are congruent. We know that this one and this one were also congruent. So if this is the same as this, we know that WM has to equal 4. And so that's going to be true by theorem. That was 6.5. The diagonals bisect each other. Okay, so let's move on to another example. This one slightly trickier. But let's draw in another parallelogram here, and this one I'm going to make slant the other way just so we see an example of that here in the notes. So this one I'm going to slant off to the left, and you'll also notice I've been drawing the horizontal parts have always been a little bit longer. Let me just do this right now just to show you what I mean. This could be rotated any which way. This is still a parallelogram. So is this. So is this. So is this, this, and this. So it doesn't always have to be oriented that way. Just so you know that. And let's draw in though on here. Let's draw in some arrows. We're going to assume that these sides are parallel here and here as well. Okay, and let's call this 4x degrees. Let's call this 60 degrees. And I'm going to say that this is E, A, S, and T. And so, over here, this is the Middle East. It's sort of in the middle of the Eastern Hemisphere. As far as I know, that's why they call it the Middle East. So, kind of cool little connection there to geography. I'm a big fan of geography. So let's see if you can figure out a few things here. Let's first figure out what's the measure of angle T. So the measure of angle T, I know based on what I said back here that opposite angles are congruent in a parallelogram. I have a parallelogram here, therefore this one is supposed to be the same as this one, and I know that this one is supposed to be the same as this one. So it actually, I think the easiest thing to figure out would be the measure of angle E. This would have to be 60 degrees. And the measure of angle T is also pretty easy to do based on a different one of those theorems. That one was that consecutive angles are supplementary. And so if this one is 60, that means that one has to be 120. I have to add, any consecutive angles have to add to 180 degrees. So this is 120 degrees right there. So that one was theorem 6.4. Write that off to the side here. That would be our justification. This one was theorem 6.3. And then if I said solve for x, figure out what x is, hopefully that would be a pretty easy thing to do because we know that consecutive angles are going to add up to 180 degrees. So we'd have the measure of angle A plus the measure of angle S should be 180 degrees. This is by theorem 6.4 again. Consecutive angles add to 180. So replace these things with what they are, 4x and 60. And now it's an algebra problem again. So let's work out our numbers here. We'd subtract 60 and we'd be left with 4x on this side. The 60s cancel. So we have 4x equals 120. Divide by 4 and you got your answer. That was ugly looking. There we go. Divide by 4. I don't want to cross out the 4x. So divide by 4. The 4's go away. You got x equals 30. So if I said to solve for x, that's all you'd have to do. Something like that. If the book says you have to solve for x, same thing. All right, let's do one more example here, and then we will be all set with this one. So I'm going to draw one more parallelogram in. This one I'm going to have leaning to the left a little bit one more time. Is there a special shape they have here? Nope, I don't see one. Okay, so I'll have to draw that in with this one more time here. And try to make them look parallel as best you can. So on the same slope or at the same slope. It's not too bad. We're assuming that this side is parallel to this side and that this one is parallel to this one right here. And I also want you to draw in the diagonals for this. So let's do that right now. So draw in the diagonals. Did not lift the pen. I did not lift the pen. Don't do that to me again. It did it to me again. I just have to. Alright. Yay. Didn't do it again. Alright. Anyway, let's give these vertices some labels. Label them up. This is a W. This is an X. This is a Y. This is a Z. And I'm going to go with M because I know that that's the midpoint. That's a parallelogram. And then everything else I'm going to leave as it is. We're going to add some things in color as we go along. So make sure you get that different color out again. We were supposed to use different color back. No, that was a different lesson. Sorry. We're supposed to use some different colors here though. There we go. And again, we're going to use that here. So I have that different color out, ready to go with that. I'm going to say that this is given to you, and this is what we're trying to prove. So we're going to do a little proof here, and we're going to try to prove that we have congruent triangles actually. So this will harken back to some stuff we did in a previous chapter. We're going to assume that if you just list out the letters in order, that's saying that the shape formed by those vertices are formed by those letters. We're going to assume that WXYZ is a parallelogram. Okay, so that's already in there. We got the arrows there. Opposite sides are parallel. We're going to try to prove that triangle WMZ, there we go, WMZ is congruent to triangle YMX. So if you look at the picture, WMZ, that's this one right here, we're trying to prove that that's the same as YMX. So why don't we use our different color and kind of highlight that first. So we're trying to prove that this triangle right here WMZ is congruent to this one right here. It's congruent to YMX. Alright, so that's what we're trying to prove. Those two red triangles are the same. Alright, so let's make our two-column proof format. We're going to do a two-column proof here. And like before, we've got our statements here, we've got our reasons on the other side. So statements go here, reasons go here. Always starting with the given part, so we're going to write down what was given to us. We're going to assume that this is in fact a parallelogram. Okay, so step 1, that's good. Now how could we prove that these triangles are congruent to each other? We have to go back to our triangle proof chapter, basically. How did we prove triangles were congruent to each other? Let's write this off to the side, that you had these 5 ways to prove congruent triangles. So ways to prove, do this in a different color too. You'll notice I'm doing that in a different color here. Ways to prove congruent triangles. Let's see if you remember. One way was, first way we learned, side, side, side. Another way was side, angle, side. A third way, angle, angle, side, and angle, side, angle was a fourth way, and the fifth way, hypotenuse, leg. So just write that off to the side as a refresher. We're going to use one of these 5 things here to try to prove that these are actually congruent triangles. And so one thing I see in here is that we could say, I think the easiest thing to notice first is that that one and that one have to be the same. That's the easiest thing that I saw, at least first. You may have noticed something different, but let's start off just for consistency. Let's all go with the same steps here. We're going to say that, well, we'd have to give this, we'd have to use 3 letters for this. We could say WMZ. If you connect the letters in that order, that's that angle. Angle WMZ is congruent to, so WM and Z would be matching up with Y, M, and X in the other triangle, Y, M, and X. Why would this be true? Those were vertical angles. So this would be our reason, vertical angles over here. So we've got one of the 3 parts. To me, it looks like we aren't going to be using side, 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 and probably not hypotenuse, leg either. I don't see necessarily right angles in any of these. And I have an angle already, so side, 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 probably not what I'm going with. There's a couple of ways we could do this, actually. We can use theorem 6.5 and say that the diagonals bisect each other. So one way I could do this would be to just draw in a mark here and here, and then 2 marks here and here, and use side, angle, side. I want to use, just for fun, just for kicks, just for a little extra practice too, the fact that we also have, if you have parallel sides, let's see if you remember something like this. Why could I draw in congruent angles there and there? I could also actually do that here and here as well. But what makes that true? Parallel sides, transversal, cutting through those parallel sides, alternates interior angles. That's another way, another possible way to prove that this works out. So we'd have to say something like WZM. Can't just use Z because I don't know if you're talking about this angle or this one or the big one. So we could say angle WZM is congruent to, and matching up in the other one would be YXM. So angle YXM has to go in that order if that's going to correspond to that one. And so this would be AIA. And then step 4, so we said that there's a couple different things we could still do here. We could prove this one and this one are the same, but we don't have angle, angle, angle. But remember, we already said this one's the same as this one, this one's the same as this one, congruent wise. So this is one option, just one of many options. I'm going to just go with this one being the same as this one. But we could also put that in here and here. So we could actually use angle, side, angle. But if we draw in like this, then we're going to use angle, angle, non-included side. So angle, angle, side is what we have here. And so we could say, based on what I drew there, WM is congruent to YM. And if you were to give a reason, you could say theorem 6.5, but I think it's better to actually write out what that theorem says, that the diagonals bisect each other in a parallelogram. And let's also put theorem 6.5 there. So either one of those is acceptable. I think better to actually describe it though when you can. And then finally step 5 now. Do we have enough? I sure do. I've got angle, angle, side matching up with angle, angle, side over here. And so I have my final step here. Let's write it in the order that it was given to me. Triangle WMZ is congruent to triangle YMZ. x by angle, angle, side, the way I've done it here. Alright, so hopefully that was helpful for you as you continue your study of lesson 6.2 here. Let me know in class if you had any questions.